Now, next up, we have something fun as well. You might see behind me, if you can still see me, it's Roland Hall over in physical sciences. Roland Hall has been there for a while, so I'm sure many alumni in the audience have, like me, taken courses there and overlooked Aldrich Park. So speaking of the School of Physical Sciences, I want to welcome to the virtual stage Professor Joe Patterson. He joins us today to discuss his work on molecular self-assembly and why it's important in understanding the origin of life. Take it away.
All right, thank you very much for the intro. Can you hear me okay? Can you see my slides?
Yes, we can hear you and see your slides.
Okay, great. So yeah, actually, I'm going to touch on the origin of life at the end of this talk, but I thought I would spend a little bit more time talking about medicine. So we're going to start there, and we'll hopefully come around to origin of life in the end. So here we're looking at the chemical structure of doxorubicin. It's a chemotherapy drug that's used to treat a wide variety of cancers, breast cancer, bladder cancer, and as many of you will already know, chemotherapy drugs do a lot of good things in terms of killing cancer cells, but they can also have a lot of toxic side effects as well. So particularly with doxorubicin, it's actually very bad on the heart tissue, and if you take too much of it, it can cause fatal heart attacks. So of course, as scientists, we want to improve drugs. We want to make them better than what we have right now. And one of the main ways that we improve the properties of drugs is actually by changing their chemical structure. So here we see an alcohol group. We might change this to an acid and then see if that modification has made this a better drug or not. And when we do that, we would call those molecular analogs. And for doxorubicin, there's been over 2,000 different molecular analogs that have been made of this compound, and over 500 of those have been tested at the National Cancer Institute. So that's really an enormous amount of research. And for a long time, that was really one of the main ways that we have of improving drugs. But in 1995, Doxil became the first ever FDA-approved nanodrug. So nanodrugs are really the use of nanotechnology to improve the properties of drugs. And usually what that means is we impart some structural feature on the drugs that's on the nano scale, so a very small structural feature that has some benefit. So in this case, we actually take the molecules of doxorubicin and we encapsulate them inside these liposomal bilayers or lipid vesicles. And you can think of these lipid vesicles as acting like a car. They help the drug get to where it needs to go and try to stop the drug from going other places that we don't want it to. And in this case, it's actually extremely effective. So Doxil is actually much less toxic than the small molecule doxorubicin. So by being able to package this inside the car, we can send this to where it needs to go. And that's really where molecular self-assembly comes in, because that's the process by which we can make these kind of complicated nanomaterials. It's the process by which molecules like doxorubicin, and molecules like these lipids, which is what the drug delivery vehicle is made from, how these organize themselves and come together to make these different types of nanostructures. And that process is complicated and it's really difficult to understand. And we use the term self-assembly because really the molecules kind of guide themselves into these structures. So we can't really, by ourselves, decide what the structure is. As chemists, we have to build molecules in a certain way and then put them under the right situations such that they organize themselves to make these structures. And that's really what my lab does. We try and understand the fundamentals of how molecular self-assembly works. And one of the ways that we do that is by imaging them with electron microscopes. So this is used in Doxil, and that came about in 1995, but this technology is used in other situations, and perhaps the most relevant of those is the mRNA COVID vaccine. So I'm sure you're all very tired of hearing about COVID, but hopefully the reason that we won't have to hear about it as much is because we have vaccines now. And the Moderna and the Pfizer vaccines are both mRNA vaccines. And a lot of the talk about this is related to the mRNA molecule. So the mRNA molecule is kind of the active molecule. It kind of tricks our cells into producing the spike protein. And then our body can build an immune response to that spike protein such that if we get infected later on, we can fight off the actual virus. But equally important to the development of these vaccines are these nanoscale vehicles that take the mRNA into the cells. So this chart that we see on the left-hand side here is a kind of timeline of the development of these vaccines. And on the left, we have the kind of development of the mRNA, but on the right, we have the development of the lipid nanoparticles. And you can see this goes all the way back to the 60s. So 1965 was when these kind of liposomes or lipid nanoparticles were first developed. And then sort of a key step in this timeline here was 1995, when Doxil, or these lipid nanoparticle encapsulated doxorubicin, were first kind of approved by the FDA. So that was a huge milestone. And it's of course amazing that we can utilize this technology in order to make vaccines. And if you were just given mRNA without these kind of lipid nanoparticles, the mRNA wouldn't make it into your cells and it wouldn't be able to trick you into producing this spike protein. So on the one hand, this is fantastic. You know, we've repurposed this technology that was developed in the 60s, used to improve cancer treatments in the 90s, and now we've used it to make vaccines. And of course, there's nothing wrong with using technology from the 60s. You know, cars from the 60s are still really great. But if you went into a dealership today and the only thing they could offer you was a 1960s technology car, you would be a little bit disappointed, right? You would be like, you know, where's my Tesla? I want something a little bit more up to date. And almost surprisingly, you know, these lipid nanoparticles are really the only technology we have for these kind of drug delivery systems, despite the fact that we've had them for such a long time. And there are a lot of reasons why it's difficult to bring about new medical technologies. But I believe one of the big reasons here is that we don't quite understand the fundamentals of molecular self-assembly enough yet. So there's a class of molecules called amphiphilic block copolymers. And these are very similar to lipids, but they're made out of polymers instead. And these have often been touted as kind of the Tesla of drug delivery systems. They're supposed to be a lot more high tech than lipids. They have improved properties, improved functionality. And although there's been a lot of amazing academic research on them, they haven't quite made it into the clinic or quite made it into industry yet. And so when I moved here to UCI, one of the things that I wanted to do in my lab was to really try and study the self-assembly processes for these amphiphilic block copolymers and see if we could use that knowledge to help advance these as drug delivery systems and many other applications too. So there's a lot of people working on these for biosensors, but also for water purification and a lot of sort of in-house applications like nanoreactors. And so usually at this point, actually, I would kind of dive straight into some results. But I think it's often a shame when we do that in science because it overlooks a lot of the really hard work that we do. It's never easy to get these kind of fancy results that we show. So I want to kind of go back to the beginning a little bit and talk about a bit of the hard work that's been done. So I moved to UCI in September 2018. And this is me standing in my research lab, or what would be my research lab eventually. When I moved here, you know, my lab was still being constructed. And so it was very exciting at this point, but also really difficult for me to kind of envision what it would be like to have a working lab with students doing experiments. And I think it's really important to always acknowledge to ourselves, you know, the kind of trajectory that we grow through. And so I want to spend some time talking about that. This is the first experiment that we did at UCI. This was actually done by one of my graduate students on RISV. And there are some block copolymers inside this vial getting ready to self-assemble themselves into nanostructures. And we actually couldn't even do this in my lab because it wasn't ready yet. But one of my colleagues, Professor Ken Shea, was kind enough to let us set up shop in the corner of his lab. And that was our home for a little bit when we started. But here is how it's going. I made this video earlier this week, and I now have an absolutely beautiful, well-equipped lab that I'm extremely happy to do work in. And a lab is not a lab without students doing research. And here you can see a time lapse of Arne making some block copolymer nanostructures. And I'm especially pleased with this little image here. You know it's a real chemistry lab when people start drawing molecules on the glass windows. And we also have some Gibbs free energy equations down here, which I'm very happy with because we're going to talk about those later on. And so it's really great to have this lab up and running and have all the equipment going. Another really key feature of my research is electron microscopy. So what we believe is that if we can look at these molecular assembly processes, we can understand them better. And we can't use light microscopes to do that because they're so small that they need higher resolution microscopes. And so we use microscopes that utilize electrons. And here you can see Paul, one of my graduate students. He's working at the TEM. These are very complicated instruments. They cost millions of dollars. And it's often very intimidating for students when you first start to use these because you're very afraid about breaking them, particularly for chemists, actually, because it's something we're often not taught about a lot in our undergraduate degrees. Here's Wyeth, another one of my grad students standing next to another TM. Here you can really kind of see the size of this instrument. So again, it's quite daunting to work on these. This is a more kind of modern design where they put the TM in a box and you can't really see how it works, but I actually prefer these kind of slightly older school designs where you actually sit at the microscope to do all your work. For these new ones, everything is computer controlled and you're in a room next door. Some of the hardest things we have to do with electron microscopy is actually preparing the samples. And this is Alana. She was a postdoc in my lab, and we can see her here preparing some examples for cryo electron microscopy. To make these, you have to work under liquid nitrogen. So inside this container here, it's full of liquid nitrogen, and she's very carefully manipulating her samples in order to get them in the right place. And a lot of what we do in my lab is famous for microscopy, but I also want to highlight that we do many other techniques too. This is my graduate student, Rain, and she established a collaboration with the Advanced Light Source and the Molecular Foundry to go and use their particle accelerator in order to get X-ray scattering data on some of these molecular assembly processes. And so this is Rain loading her samples into the particle accelerator, which again is a really kind of cool thing to do. This is my whole group, and I just wanted to take this opportunity in the middle to kind of thank everybody for really all the hard work that they've done. And I could tell you a story about any one of these people, you know, about the trajectory they've taken. But what I want to do today is kind of focus a little bit on Arne and the work that he's been doing since he started here at UCI. So this is a picture of Arne in the beginning when he was trained to do some of these electron microscopy experiments. And as I said in the beginning, I think this can be very intimidating. So the microscopes cost millions of dollars. And particularly in my lab, what Arne was working on was some liquid phase electron microscopy. And we use these holders that have many different parts, and these cost hundreds of thousands of dollars. And everything is very easy to break and very difficult to put together. And probably at this point in the beginning, it was difficult for him to believe that he could ever become an expert in this technique. But if we work hard at things, if we come in every day and put the hours in and study, you know, we can really learn anything we want. And here again is another time-lapse video of Arne disassembling and cleaning and then reassembling this holder, which is something he has to do as part of his research on a regular basis. And again, you can see now here that he's really kind of mastered these skills. He's sitting back and relaxed and very confident with everything that he's doing. And I really wanted to highlight this because, again, it really shows all of the hard work that goes into the great science that we have. Behind any kind of picture or image or data set, there's kind of hours and hours and hours of people working hard and being very precise with every single movement. So right at the end of the video, Arne is off here. He's going to go off to the microscope and start collecting some data, which I'm actually going to show you. But I also want to highlight that we have products for this data too. So Arne has published 3 first author papers in his PhD so far, which is really absolutely amazing. And we'll look at some of the data from them in a second. But one of them is actually a review paper, which is the title of this talk. And one of the points that we make in this review paper is that we believe that electron microscopy is so important for understanding molecular self-assembly because it allows us to look at things that we've never been able to look at before. Often in science, we talk about testing hypotheses. Hypothesis is a statement about how something works, and then we want to test, is that true or false? But often we forget to talk about how do you generate a hypothesis in the first place? How do you come up with a new idea that we don't already know? And we think looking at how things work, taking pictures of things is one of the best ways of generating hypotheses because often things don't look the way you expect them to. So here we're going to look at a couple of movies of these molecular self-assembly events. There are polymers, amphiphilic block copolymers in this solution, and they're going to start forming these nanostructures. And so what we'll see is these really sort of appearing out of the background from the very smallest size, and then they start moving around and fusing together to make these solid materials. And it may or may not be clear to you, but to me and Arne, when we look at this in the very early stages of this movie, the way these particles are moving around and the way they're interacting is not what we expect. There's too much motion and too many dynamics for these to be solid materials. At the end of the movie, they look a lot more solid, but in the beginning, it looks a little bit different. I'm going to show you another movie here where maybe this will be a little bit clearer. If we look at the way these materials form, the way these structures interact with one another and grow, they look very liquid-like. It's really important to remember that the definition between a liquid and a solid is about how molecules are moving. In solids, molecules don't move very much, but in liquids, they move a lot. That's why liquid water will pour very easily, but solid water, ice, holds its own shape. So when we look at these movies and we see these nanoscale materials, we were thinking to ourselves, these look more liquid than solid. And that was really not a part of the theory for how these materials should form. So that was how we kind of generated this hypothesis that these structures might form liquids before they form solids. And so then, of course, we had to go about testing this hypothesis and coming up with a theory for how that works. So before I go on here, I want to say, don't worry, there's not going to be an exam at the end of this talk. Usually when I show a slide like this with a lot of math to my undergrads, there's a sharp intake of breath, but there's no exam at the end of here, so we don't need to worry about this. But what I do want to just establish here is that we actually have a very good mathematical explanation for why these structures should form liquids. These are based on Gibbs free energy calculations, and that was what was drawn on the window that I showed you earlier. And these calculations match up with this figure, which contains a lot of experimental data. So this was the data that kind of proved this hypothesis, but what does this mean? So what we've established now with our theory is that these amphiphilic block copolymers, which we knew we could already form these kind of solid phase structures, which are used for drug delivery, but they can also form these kind of liquid droplet structures, and we can transition them backwards and forwards to one another. So one of the challenges with using these solid phase materials for delivery system has always been getting lots of drug inside them. You have to really push the drug if you want to get it inside these solid materials. But what we found for these liquid phase materials is they actually act more like a sponge. They kind of suck up really any molecule. And we've shown in our lab now that these will suck up lots of drug molecules. And we believe that we can use these and then convert them into the solid phase material, which we can then use for drug delivery systems. So this is the project that Arne's really established and what he's working on in the future. And very recently, a new graduate student joined my lab, Nahal. And Nahal previously, as an undergrad, worked on a project to do with oil spills. And she came up with the idea that maybe we could use these liquid phase materials to suck up the oil, and then we could convert them into the solid phase material and use that to remove the oil from the ocean. And I think this is an amazing idea. And again, something that we're now pursuing in the lab. The other thing that we've been able to show, or Arne's been able to show, is that from these liquid phase polymer materials, which we call coacervates, we can actually make many, many different types of solid phase structures. We can make fibers, microporous membranes, nanoparticles, and also microparticles. And so with these, we think this really opens up this to a whole wide range of applications that go far beyond drug delivery. And I think this is a great example of how science works. You know, we started out with an observation. We observed something we didn't expect, and that allowed us to generate a hypothesis. We then did a lot of experiments to prove that hypothesis, and then that is now enabling us to go down and investigate new applications. So how does this relate to the origin of life? So I'll do this very briefly, so I'll try and keep us to time a little bit. But basically, in origin of life research, molecular self-assembly plays a role because at some point you have to form a structure. You know, really what kind of defines me as being me is the fact that the chemicals inside my body are staying in there. And often the origin of life is really thought of as a problem about what was the first structure that formed that contained chemicals. And for a long time, these kind of solid phase vesicle structures, just like the liposomes or just like these polymer structures, were thought to be the very first structure that formed. But again, one of the challenges with these that we know is if you want to get a lot of chemicals inside them, you really have to push them inside. And at the point on Earth where life was just starting, it's not really obvious that there would have been any huge driving force to push molecules inside. So more recently, people have started talking about these more kind of liquid phase materials, these coacervates as perhaps being the first structure. And the reason people like these is because, like I said, they're sponges and they just kind of suck up everything near them. And what we've done in our research for the first time is we've provided a mechanistic connection between these two structures. And I think going forward, this provides a lot of exciting future research for us to do in thinking about how the origin of life occurred and how these two kind of very fundamental structures that people study are related to one another. So today, I really just told you about one story we have going on my lab to do with block copolymers, but we work on many other different types of materials, and each one of them has their own kind of story about discovering something new, testing hypotheses, and then enabling new applications. And in addition to that, my lab is really focused on improving electron microscopy as a technique, because I really believe that the more things we can look at with higher resolution, with better clarity, the more things we'll be able to discover, and that's going to lead to much more innovation in science. And then very finally, I just want to finish up to also say that it's a lot of fun being in a research lab. In addition to all the hard work that we do, we always find time to have fun together. And here are a few examples of that. And then finally, again, I want to acknowledge everybody in my group. I also want to acknowledge all the funding agencies, which have been great, all my collaborators. And then finally, I want to say a really big thank you actually to the staff at the Irvine Materials Research Institute. So these very fancy electron microscopes and many other pieces of equipment that they have there, it would be impossible for me to have these in my lab. They're too expensive. They require a lot of maintenance. They require experts to really look after them and train the students every day. And so if it wasn't for the amazing staff that we have at the Institute, I wouldn't be able to do any of the research in my lab. And I think this is true of many other groups at UCI. So they're a huge and really important part of the team. And I just wanted to really finish by thanking them. And then I'll say thank you to you all for listening. And I'm happy to answer any questions. All right. Well, lots of nice comments in the chat. Thank you very much. I don't see any questions in the Q&A, so I'm happy to wrap things up. I think I got us back on time.
That was an amazing presentation. Thank you so much, Joe. That was a great look, and I like how well-rounded it was, describing the experience it is to be a UCI professor and researcher. That's fascinating. Thank you so much.
Thank you. Thanks.